So let's now take this a step further and consider if we're going from hexadecimal to decimal. I kick this down the line. My favorite hexadecimal number is BAD. So hexadecimal values use an alphabet of 0 through 9 and then A through F. So 0 through 9 stands for 0 through 9, and A is a 10, a B is an 11, a C is 12, D is 13, E is 14, F is 15. Make sense? All right. So for hexadecimal, this is the ones place. This is the 16s place. 256, I think. Yeah, this is the 256 place. So you can think of this as also being the 16 to the 0, 16 to the 1, 16 to the 2, all right, so the first thing you need to do is you need to convert the letters into the numeric equivalent so we can do math. Because you can't say D times 1. That doesn't make any sense. Right? So a D is a 13. So if we rewrote this, BAD is actually the value 11, 10, 13. Make sense? So now we can do the exact same thing we've done before. So this is 13 times 1 plus 10 times 16 plus 11 times 256. Should be 2989, I think. 2989. Make sense? All right, let's do another one. $241, is that a legal hexadecimal number? Yep. It uses only the alphabet 0 through 9 or A through F. Just happen to not use any letters. You don't have to have letters in a hexadecimal value. So 241 converted to hex, that's going to be 1 times a 1 plus a 4 times a 16 plus a 2 times a 256 for 577. Make sense? All right, so let's have you go ahead and do one. All right, so go ahead and convert F7B from hexadecimal to decimal. Take a couple minutes. This is practice, not another quiz. So we'll go ahead and rewrite these guys as an F is a 15, a 7 is a 7, a B is an 11. So this is going to be 11 times 1 plus 7 times 16 plus 15 times 256. 3,963. Make sense?
Yes.
Okay. So we're going to go base 34 to decimal. FAT. All right, so go ahead, take a minute, try to convert the base 34 number FAT into its decimal equivalent. So what I'm going to do here real quick is I'm just going to type out the alphabet, A, B, C. All right, even though that's not the whole alphabet for base 34, this will get me far enough in. So this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. T is 29. Okay. So this is 15, 10, 29. All right, so then down here, and this is the ones place. This is the 34s place. This is the 1156 place. So this is 29 times 1 plus 10 times 34 plus 15 times 1156. 17,709. All right, make some sense? So at this point, the hardest part of doing any of these is going to be converting a letter into its numeric equivalent. You start getting deep into the alphabet, and you got to be a little careful to make sure you map it to the right place. But we notice now that converting between any of these bases is the identical pattern, right? Every single one of them, the exact same pattern. Why would we use a big base? What's the advantage of, say, a base 34 over a base 10? Is it just so we can give you difficult math problems in class? Okay, so forget about the bits part of it for a second. Just in general, we're used to base 10 numbers. So we can represent large base 10 numbers in a bigger base in a smaller footprint. So 17,709 we could represent as FAT. FAT is shorter than 17,709. It takes less space to write that, right? So if I write FAT out and I say that's a base 34 number, I'm storing the exact same information. I'm encoding it in base 34 rather than encoding it in base 10. Base 10 has a larger physical footprint, right? Now, base 2 typically has the largest footprint. The only footprint bigger than base 2 would be base 1. What are the legal digits in base 1? It's just 0. You just count the number of zeros, and that gives you your, so that's, nobody uses that. All right, so for base 2, though, we could represent, if we had to represent 17,709 from decimal into binary, it could be a pretty big binary number, right? Big old long string of zeros and ones. Not real friendly for us. So for human beings, we like passing things around in a certain package size. And then we like to, and then a computer likes it in binary, and then we have a couple of intermediary things. So earlier we talked about kind of the popular numbers for computers are binary at the end of the day. The computers are always operating off of binary. But then we have octal and hexadecimal are other bases for those guys. Now, let's just talk about hexadecimal for a second. So hexadecimal being base 16 would allow us to represent fairly large numbers in fairly small footprints, right? Be even nice and compact in size. What kind of values in a computer are going to start getting pretty large from our perspective? What kind of base 10 value would start getting pretty large in a computer? Let's go right here. Let's think about a hard drive. How big are our hard drives today? You get a terabyte, and they get bigger than that, right? Like maybe your average new laptop has a terabyte in it. Now we kind of started going sideways a little bit, where maybe a brand new nice laptop has either a 256 gigabyte or a 512 gigabyte hard drive in it. Why is it getting smaller? Now they're getting faster, right? The technology has flipped. So a nice laptop now has a solid state hard drive in it, which is a lot faster. I mean, way, way, way faster than a traditional hard drive. But you pay for that. So you typically have less capacity to keep the price of the machine somewhat reasonable. Okay? But let's just operate off of our 1 terabyte value. That'll give us a good example here. So we have 1 terabyte. Now, we talked about conversions last time, right? We have we went from bits to bytes and all those things. We did that last time, right? Didn't we? You sure? Are you lying? Are you still lying? You're on the T, dude. Okay, so let's talk about that then for a minute. I love this slide. This is going to be a good one. How many of you have internet at home? Many of you have internet in your apartments or something like that. What's the speed of the internet that you have? Who? 20 gigabyte? 7 gigabyte? 70.
Yeah.
Gigabyte?
Yeah.
70 gigabyte. All right, well, it's not that. We'll talk about that. 50 megabytes per second. So 50 megabytes per second. Okay. It's also not that. What else? We got 2 speeds out of the whole class. So you either have a cable modem or you have DSL through AT&T or something like that. Okay, so the two of you are trying to describe cable modem speeds to me. You're just not describing them accurately. Anybody else want to throw a speed out there? Can anybody get a speed right?
It depends on the weight on the internet that will determine the speed.
The advertised speed that they're selling it to you. This isn't the advertised speed they sold it to you. For yours, it's almost the advertised speed they sold it to you. Little niche. Yours isn't even close. But the good news is this is common. It's unfortunate, but it's common. Because wouldn't you say that as master's degree students in information technology, we should be like really up on this stuff, right? The speed, how things move across the network, that's kind of our thing, right? So at the very least, we should kind of know what kind of internet speed we have at home. So I assume, so you live in the area here?
West Coast.
Okay, so your provider Spectrum, right?
Yes.
Okay. Your internet is not 50 megabytes per second. It is 50 megabit per second. Small b. Okay, we'll talk about the difference there. You also Spectrum? All right. Yeah, yours is megabits as well. Trust me. Well, they might have said something to you. You don't have 70 gigabytes per second. You don't have 70 gigabits per second. You have 70 megabits per second. All right. The fastest internet you can get as a consumer in the Milwaukee area, and really anywhere in the world right now, is you can buy 1 gigabit per second. Downtown Milwaukee has 1 gigabit per second from AT&T, and several cities have 1 gigabit per second through Google. Google has a connection, but that's gigabit, not gigabyte. Let's talk about the difference there. So we're going to say sizes, because sizes, speed kind of means the same thing, because what we've done here is we just put a little PS at the end of it, per second. What's the speed per second? That's the amount of data it can transfer per second. So we're going to have two different columns here. All right, so this column, we're going to have a bit. A bit is a 0 or a 1. We already discussed that, right? Over here, we're going to have a byte. What's a byte?
8 bits.
8 bits, okay? So let's do our bits here first. So now we have, so the next thing is a kilobit with a small b. A kilobit is, how many bits are in 1 kilobit?
1,000.
Almost. 1,024. So we have 1,024 bits in 1 kilobit. Then we have a megabit, small b. How many kilobits are in 1 megabit? 1,024 kilobits in 1 megabit. Then we have a gigabit. How many megabits are in 1 gigabit? Starting to see a pattern here. 1,024 megabits in 1 gigabit. Technically, the next thing would be a terabit, although nobody talks about things in terms of terabits at this point. Probably, we roll down 10 years in the future, our internet connections will probably be in terabits per second. But whatever, this is 1,024 gigabits. Notice small b means bits. Big B means bytes. Okay? So now we come over to this side. A byte is 8 bits. A kilobyte, big B, is 1,024 bytes. A megabyte, big B, is 1,024 kilobytes. A gigabit, big B, is 1,024 megabytes. A terabyte, big B, is 1,024 gigabytes. Make sense? All right, so if we go back over here, your 50 megabit per second internet connection is equal to 50 divided by 8, 6.25 megabytes per second. 6.25 megabytes per second. That's your internet, okay? Your internet, 70 divided by 8 is 8.75 megabytes per second. Now, why do you think Spectrum sold you 50 megabit per second instead of 6.25 megabytes per second? Why do they advertise it as 50 megabit?
Because people don't know the difference. It looks better.
Bigger, looks bigger, right? 50 is bigger than 6.25. Normal consumers don't know the difference, right? You might say, why didn't they go beyond that? Because all the commercials, next time the commercial's on for Spectrum or something like that, watch it. They don't say megabit. They say meg. 100 meg internet. So they even use like kind of a slang term for it, right? It's like, oh, it's 100 meg internet. Okay. It's megabits per second. How long ago did you sign up with Spectrum for 50? A while ago?
Yeah, back when they were like Time Warner.
Okay. You're going to thank me for this later. Call them up, make sure you switch to. Are you officially over on Spectrum yet?
I've actually switched to Spectrum.
Call them again. You should be getting 100 megabits for the same price as you're getting your 50. Just make sure they've switched your circuit over to it. Yeah, Time Warner or Spectrum, their base internet now is 100 megabit. That's their cheap internet, is 100 megabit.
I get it.
You get 100?
Yeah.
I thought you said 70.
At the beginning, it was 7. Now they are great.
Okay, yeah, so that's fine. So we have 100, so 100 divided by 8, so you get a theoretical maximum of 12.5 megabytes per second. All right, so make sure you make that call. Won't cost you anything more. That's just what their new base internet is, and it's possible you're actually already getting it.
Okay.
Just in your mind, they sold you 50 megabit per second, then they just bumped everybody. So I have Spectrum. I get 300 megabit per second from Spectrum, but I pay for their faster one.
Okay.
Yeah, so they have two. All right, but regardless. So if we had gigabit per second, if you live in downtown Milwaukee, you can get gigabit, and pretty soon it's going to be up here. They've already AT&T's already been up here, kind of surveying and stuff. So gigabit internet. How many megabytes per second is a gigabit internet? So 1 gigabit internet is equal to how many megabits? Small b. 1,024 megabits per second. That's what a gigabit is. It's as if Spectrum sold you 1,024 megabits per second. Okay? Which is equal to 1,024 divided by 8, 128 megabytes per second. Theoretical maximum. Theoretical maximum. For any of these internet speeds, you're at the mercy of how fast wherever you're downloading from can serve it to you. Make sense? So you'll cover this stuff in your networking course. I'm not going to belabor this, but now hopefully nobody in here has had the networking course. Is it 540? Has anybody here had the networking class? Don't admit it if you have, because you should have known this stuff. Okay. You'll talk about that stuff in more detail in there. The reason I introduce it here is to give us a point for what we ran into up here. Why do we need bases for representing larger values? Do we have somebody who took it and...
Oh, no. He's taking it. So.
Who's the teacher for it?
Just hit the nail on the head.
What's this?
I said you just hit the nail on the head. That's
why
teacher.
everyone is talking about that class.
Oh, hold on. Do I need to pause for a second? Okay. So, punchline here. When you take the networking course, you're going to learn about how stuff actually travels over the internet and all that other garbage. It's an important concept. Learn it in there, whatever. The reason I bring it up in here is we wanted to understand these different sizes because that means something to us in terms of why do we need large numbers? Why do we need something like hexadecimal to think about numbers? So what we want to do is we want to think about a 1 terabyte hard drive. Okay, 1 terabyte hard drive. Now, let's think about this in terms of what's a file system? Okay, that's an example of a file system, right? So he gave an example of NTFS. How many of you use NTFS? How many of you is that your file system of choice? How many of you don't know?
I've heard.
Most of us, right? How many of you are Windows users? You use Windows 7 or newer. Actually, you use Windows XP or newer. Most of you use NTFS. All right, that's your default file system for Windows. NTFS is New Technology File System. What other file systems have you heard of? There's another one that most of you probably use. You probably have access to it on your keychain right now. How many of you have a USB drive or external USB hard drive? Like one of the USB jump drives, those guys? Lots of you have those? What file system did you choose to put on that? I didn't. It came with it. Okay, it comes with FAT32. File access, file allocation table, 32-bit.
This one comes with Apple or
Now the USB hard drives and USB sticks will be pre-formatted FAT32, and Windows-based operating systems prior to Windows XP, the consumer side would have been FAT32. Now, interesting factoid here. How many of you have a USB jump drive or a USB hard drive that's at least 128 gigabytes? Actually, it doesn't have to be that big. How many of you have one that's at least 8 gigabytes? Most of you, right? How many of you ever tried to put a 5 gigabyte file onto an 8 gigabyte jump drive? It should fit, right? What happens? What error message do you get? No space. Why? I got 5. I want to store 5. I have 8. There's room. If you got a bucket capable of holding 8 gallons and you dump 5 gallons into it, it fits. But why can't you put a 5 gigabyte file into an 8 gigabyte jump drive?
there's some ways.
Say this again. No, you actually have enough. Physically, there's enough space to hold 5 gigabytes. So you're suggesting you actually are out of space, even though you should have space. So here's the thing. If you have a 128 gigabyte jump drive, that 5 gigabyte file still will not fit. But you have 128 gigabytes, way too big, right? It'll still say you're out of space. Why is that?
When you're transferring, the file system on the USB doesn't really recognize it.
A file system is a tool that an operating system uses to manage files and directories. FAT32 has a limitation that the largest file it can record is 4,096 megabytes, 4 gigabytes. Any file, any single file bigger than 4 gigabytes cannot be stored on a FAT32 file system, even if you have plenty of space. Now, if you have a directory with 5 gigabytes of stuff in it, but no individual file is bigger than 4 gigabytes, it'll fit, no problem. The issue is when you have a single file. A lot of times it might be like an ISO, a CD image for like a Linux distribution or something like that that's really large, and maybe you have or you maybe have a Blu-ray rip of some movie. Maybe it's the latest Star Trek movie. That might be a really big file, bigger than 4 gigabytes. That won't fit. So what are your options? Well, you can format your USB stick to be NTFS. No problem. But if you formatted your USB stick to be NTFS, what did you just do? You limited yourself. What was the limitation you put on there? Can't stick it into a Mac. So if you have a jump drive, a USB stick, that's formatted NTFS, which you would have had to choose to do that. Takes no time. Just right-click on it, say Format on Windows, choose NTFS as the file system. Format it in a couple seconds. And now you can store 4 gigabyte files, 5 gig files, 10 gigabyte files, no problem. But you stick that into a Mac. Macs can't, they don't speak NTFS. NTFS is a proprietary file system from Microsoft. Apple computers will try to format it. Like, well, I don't know what this is. Do you want to format this drive? Make sense? So you'll add that limitation. If you don't care, it doesn't matter. Format an NTFS and move on with life.
USB stick, if you say put it in Windows or in my computer now, and I change the format to NTFS, doesn't work in app?
Correct. Won't work on Apple.
Apple?
Or Linux. Linux does have experimental support for NTFS, so it'll sort of kind of work. for read-only. There are ways to get NTFS working in other operating systems read-only, but writing to it is pretty dangerous. You might corrupt it.
How are you turn it back to
Format it again.
from Windows?
Yeah. Yeah, Windows, if you format a drive on Windows, you can format it NTFS or FAT32. Either one of those. FAT32 has a limitation of maximum file size is 4 gigabytes, but it has the flexibility that you can take that to a PC or a Mac and it'll work, because they both know about FAT32. NTFS only works on Windows machines, but will allow you to have file. I think the maximum single file size might be like 16 terabytes for NTFS. I might be wrong on that, but it's way bigger than 4 gigabytes. I think it is 16 terabytes, but whatever. Make sense? Okay, so these are interesting limitations, and these are the types of things that will play into your careers, right? Because when you're working on machines, copying files over, doing stuff, you might run into that situation where you have a USB drive that you're trying to put a file onto, and like, this is a 1 terabyte external USB hard drive. Why can't I put a 6 gigabyte file on there?
But it doesn't really make sense why a USB drive would be FAT32, but then still have like a capacity of like.
Well, the idea is that a USB drive is portable, so you might want to stick it into different kinds of machines.
Oh.
So the default is FAT32 file system port, not because it's USB, but because it's portable, they figure, well, you probably want to be able to stick this in a Mac and open your Word file,
Right.
or stick this in a PC and open your Word file. So we better choose a file system that's compatible with both.
So that
If
means
you have your laptop with Windows on it, throw NTFS in it. You're not going to plug that hard drive into other machines.
then what if you format it to NTFS, you put something that's worth let's say 10 gigabytes on it, you try to format it back to FAT32 erase?
Yeah, everything that was on there will be gone. But you can switch it back. I mean, switching to the new file system just changes the software that governs that hard drive.
Okay. What about an external hard drive, though? What kind of file?
Typically, external hard drives will default to FAT32 because they figure you're going to be plugging it into different machines.
Right.
But if you're not, if you're always going to keep it plugged into your Windows machine, reformat it in NTFS, and then you don't have file size limitations.
Okay, so that means that even if I have a 50 gigabyte external hard drive, I cannot put more than 4 gigabytes.
In a single file.
Oh, in a single file.
Single file.
Okay.
You could have 30 4 gigabyte files, but you can't even have one 5 gigabyte file.
Okay.
Because the file system can't allocate for that much space. That makes sense? It's just a limitation of the file system.
That makes sense.
Okay. And then the Macintosh systems now use a Unix file system, a UFS, which because Apple stole OpenBSD Unix, and so their file system is based off of Unix. Same thing in Linux. So you could think of Mac OS as being very similar to Linux with kind of a foo-foo-y front end on it to make it look like Apple, which is fine. I mean, it's just a computer. You figure out how to use it and you move on with life. Okay. So the reason we care about this in here, so let's think about this in terms of megabytes. So how many megabytes is a 1 terabyte drive? So that is 1 terabyte is 1,024 gigabytes, which is 1,024 megabytes. So this is the number of megabytes on a, actually I want to go even bigger than this. Let's go to bytes. So that's megabytes, that's kilobytes, that's bytes. All right, so a 1 terabyte hard drive can store this many bytes. A lot. Now, just as an example file system might say that the smallest chunk of data, we spent the last several minutes talking about what's the largest chunk of data that you can store on a FAT32 file system. We said that's 4 gigabytes. But what's the smallest chunk of data? On hard drives, that's usually something called block size. So let's assume the block size for this is 4 bytes block size. So that means that if we take that whole number, we divide it by 4, this is the number of unique storage locations on a 1 terabyte hard drive. 274,877,906,944. Make sense? That's a lot. Big number. So, to address that, if you need to store a piece of information, so you're going to store, and we can store the smallest bit of information, smallest piece of information we can store on this example file system is a 4-byte chunk of data. Right? So if we have 17 bytes that we need to store, we're going to store that in 5 blocks. We can fit 16 bytes in 4 blocks. Then we'll only use a quarter of that last block to hold the extra 1 byte. So we'll have some wasted space in there. Not the end of the world, just a little bit. That's why you got to pick your sweet spot. What's the smallest we'll allow a block to be to make sure we don't have too much wasted space? Yet, if we have blocks, you might say, well, why shouldn't blocks be 1 byte in size? Heck, if you want to be completely unwasteful, we could say a block is 1 bit in size. So how many bits are in a 1 terabyte hard drive? That's the number of bytes. That's the number of bits. A lot. Now keep in mind, if we're going to store stuff in this hard drive, we can even look at it in the worst case, because this will give us a good example. Let's just say that we really, really, really don't want to be wasteful. I promise you this is going to be horribly inefficient. That's why file systems don't store things 1 bit at a time. It'll be really, really, really slow, and will take forever to look stuff up. So read-write times will take forever. But this number is bits. So if we use this as our example, just to really exaggerate it, this is so we're going to say we have a 1 bit block size. That means we have this many unique storage locations on our hard drive. So what's that? 8,796,093,022,208. Big number. All right? And this is going to be indexed between bucket 0 and 8,796,093,000,000 or 8,796,093,022,207. So we have that many buckets, starting at bucket 0, then bucket 1, then bucket 2, all the way up to bucket 8.7 trillion. Make sense? So when we store stuff, we have to look up the address where we're going to put that on the hard drive. Right? Now, you take a big city like Chicago or New York. Each house has a unique address, right? There's a zillion houses. Now, in cities like New York, well, really any city, any human city, there's more than just a number that goes to an address, right? It's a house number plus a street, right? That way, it's, so you might live on 123 Elm Street, something like that. In computers, we're indexing those things, those houses, just by number. This is house number 1, 2, 3, 4, 5, 6, so on and so forth. Make sense? This is how many houses are in this really inefficient hard drive with a 1-bit block size. So that means if I want to store some piece of information in house number 9, I'm going to have to go and search where house number 9 is on that hard drive and put my piece of information there. If I want to store that piece of information in house 8.72 trillion, I'm going to have to seek to that memory address on there to store my piece of information there. Now, wouldn't you say that this isn't a really convenient number to work off of? Humans don't like speaking numbers this large, right? This isn't a fun number. You got to think about it to say this number. So would you prefer to represent this number in binary? No, because it just got way worse, right? That number in binary is some ridiculously long string of zeros and ones, right? Ridiculous. So, having said that, we maybe would go the other direction. So rather than going from base 10, which this number is, to base 2, which we decided would be worse, maybe we go from base 10 to base 16. Okay? Because this number in base 16, while it still might be a scary looking number, would be a smaller number. That make sense? We take smaller footprint. Okay? That's where larger bases come in. All right. Now, the reality is, like I mentioned, in computers today, you would never have a file system with a 1-bit block size. You would want something bigger than base 16 to address it. It just so happens that a 1-bit block size would be so inefficient that you'd rather have a little bit of wasted space. Who cares? Who cares about 3 bytes of wasted space every now and then? Not a big deal. Okay. So typically you'd have a 4-byte block size or something like that. So you'd cut this number down quite a bit. Still a big number, but a number that could be comfortably represented in base 16. So we use base 16 to keep track of memory addresses in our computers. So rather than saying this is house 0, this is house 1, this is house 2, this is house 10 zillion, this is hexadecimal value this, hexadecimal. It still maps. No, hex is 16, base 16. Well, no. So house 274,329,000, blah, 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 would be a much smaller value if I represent it as base 16. So I would say here is the address of that house in a nice, small chunk. It's the same number. Whether we say it in base 16 or we say it in binary or we say it in base 10, they're all the same number. We just have to know how it's encoded so we can pull meaning out of that, right? But if we're storing it in base 16, that becomes meaningful to a computer because we can, you could say a base 16 number more quickly than you could say the equivalent base 10 number, because a base 10 number is going to be this big scary thing. Well, shorter. Yeah, base 37 would be even better. Nice little tiny number, right? But we'll see that base 37 isn't as friendly. It's a less friendly base, and we're going to see that coming up next. All right, so we kind of gather the reason for having those large bases. All right, in general. Bigger the base, the smaller footprint large numbers are represented as. Smaller the base, bigger those numbers are.
Bigger space.
Bigger footprint. A number is a number. The number 10 is the number 10 regardless of what base we store it in. Okay? So the binary version of 10 is still the same thing as the decimal number version of 10, which is still the same thing as the hexadecimal version of 10. The difference is how long does it say to say the number? How many alphabet characters does it take to express it? Okay? So now let's go back the other direction. So let's convert from decimal to binary. So let's say we have the decimal value 89. And we want to convert that guy into binary. We already went the other direction, right? We looked at binary numbers and octal numbers and hexadecimal numbers. We converted those to decimal. But sometimes we're going to be sitting there with a decimal number and we need to get the equivalent representation in binary or hexadecimal or octal, those guys. So we want to convert 89, the decimal value 89, to binary. And the way we're going to do this is with something called Modulo. Sometimes it's expressed as modulus. You might know it by something called long division. Remember long division from your math classes? Oh, you didn't love long division? Really? What grade did you have long division in? So here, I believe that I had long division in 3rd grade. I'm more asking, is it the same? You're in Nigeria, right?
Yeah.
Was that about right when you first learned long division? What did she say?
Because I'm trying to like think about like the equivalent of the grading system here.
Yeah, it was always so here's like long division. If I take the number 5 and I divide it by 2. In long division, 2 goes into 5 2 times. So this is 2, remainder 1. Right? That's long division. Also known as integer division. Okay, so in the States, we learned that around 3rd grade when we do long division. At least that's what I recall. I assume it hasn't changed drastically, but around then. And nobody likes it because when you're in 3rd grade, you're young and stupid, right? Okay, you care more about riding your bike and throwing dirt at people. This is the whole right. That's what 3rd graders do. They're like little idiots. They're basically just like short versions of what's that?
Yeah, different.
What are 3rd graders doing in your country? Well, not watching Star Trek. We already covered that. You're both Saudi? Yeah. I was looking up. I think maybe one of the. I think your media is pretty. They're very careful what they put on media in Saudi Arabia. Is that accurate?
Yeah.
Like they censor quite a bit of stuff. So I think that might be the reason why you haven't seen Star Trek. It really is baffling to me. It really was. I looked it up.
So yeah, I would. If you want me to see it, I will see it.
No, I really don't care. To be honest, I'm not even a fan of Star Trek. I don't even. I'm a Star. Here, it's like you're either Star Trek or Star Wars. Very rarely is somebody a super fan of both. You've heard of Star Wars?
Is it movie?
You've heard of Star Wars. Please tell me you've heard of Star Wars. Luke Skywalker, Han Solo, Darth Vader, lightsabers. Oh my gosh. Okay, in any case,
Is it movies?
these are movies.
Movies? No.
Like super famous, super famous. Okay, but regardless, so I mean,
Like movies.
yeah, it doesn't matter. We're not even talking about whether you like it or not. So if somebody here might say a joke and reference Star Wars or reference Star Trek, and pretty much everybody would know what they're talking about. They might not like the show. Like I don't really like Star Trek that much. I like Star Wars a lot more than Star Trek. But if somebody references Star Trek, I pretty much know what they're talking about. You get what I'm saying? It's like common knowledge.
Yeah.
Like you know what a Big Mac is. You've heard of a Big Mac, McDonald's Big Mac, the sandwich?
No,
You know what a McDonald's is.
I know McDonald's, but Big Mac.
Okay, fine. You know what McDonald's is.
Yeah.
Okay. So it would be like, Star Wars here would be like somebody saying McDonald's. They're common knowledge things. Or in technology, it'd be like somebody just Google it.
Yeah.
You see what I'm saying? Like Star Trek, Star Wars would fit into that category here. So really, I mean, I understand. It was really just surprising that, and I'm sure there's plenty of other examples you brought up. There's probably things from your country that you take as common knowledge that I have no idea about, right? Like I imagine, like many of you are either cricket fans or soccer fans. There's probably some big name, famous cricket players that many countries in the world is just common knowledge. Like this dude is really good or something like that. Where I've probably never heard of him, right? Because it would be a similar thing. So really, the only famous sports people that I'm going to hear about are ones that came over to the United States to make the big money, right? They came over here regardless of the sport. Like you've heard of Tiger Woods, right? You've heard of Tiger Woods before? Okay. But you don't follow golf, do you? Did you even know he was a golfer? Yeah, you just heard of Tiger Woods because he's just like Michael Jordan. Yeah, you know, they're just super famous to the point that everybody knows who they are, regardless of whether they know what they do. So I'm sure you have the equivalent of soccer players and cricket players that are just like that I've never even heard of. You know, something like that. I do find where the breakoff is, though. How many of you have heard of Roger Federer? How many of you, well, let's go the other way. How many of you have never heard of Roger Federer? A couple of people. That's more common. So Roger Federer is kind of like the Tiger Woods or the Michael Jordan of tennis. Super, like the greatest ever. You know, has won more top tournaments than anybody. But it's very interesting to me that more people don't know who he is than like Tiger Woods and Michael Jordan, when really he's at that same level. Yeah. So I don't know. It's just, I think we all take for granted what's common knowledge in our worlds, right? Yeah. At least you've heard of McDonald's. Class would be over if you had said you never heard of McDonald's.
No, don't worry about it. McDonald's, I know it.
Yeah. Well, I don't know if you want to call it food. I don't even care if you like McDonald's. You just heard of it.
McDonald's is everywhere.
It is very interesting. I was in Israel, not this past June, but the June before that, and maybe your culture is similar, where they don't do dairy and meat in the same dish,
Yeah.
something like that. So there is no such thing as a Big Mac in Israel, because a Big Mac has meat and cheese on it. So there's no such thing as a cheeseburger over there. Yeah, so they had something called, I think, the Big American or something like that, which was a burger with the Big Mac sauce but no cheese. And you learn something new every time you go to a different country. I just find that fascinating. I want to go to. I've never been. I want to go to Saudi Arabia. Be a cool place. They have some nice golf courses in Saudi Arabia. Very nice golf courses in Saudi Arabia. Okay, so swinging back into this. So we're talking about long division. This is something we use to convert values. So what we're going to do here is when we try to get the binary version of the decimal number 89, we're going to divide 89 by 2 multiple times. 89 divided by 2 is 44. So this is 44. 44 times 2 is 88 with a remainder of 1. 44 divided by 2 is 22. 22 times 2 is 44 with a remainder of 0. 22 divided by 2 is 11. 11 times 2 is 22 with a remainder of 0. 22, 22, same number. So 22 minus 22 gives you 0. 11 divided by 2 is 5. 5 times 2 is 10. 11 minus 10 is 1. So it's a remainder of 1. 5 divided by 2 is 2. 2 times 2 is 4. 5 minus 4 is 1. Remainder of 1. 2 divided by 2 is 1. 1 times 2 is 2 with a remainder of 0. 1 divided by 2. How many times does 2 go into 1? 0 times. 0 times 2 is 0 with a remainder of 1. We know we are done when we finally end up with a 0 there. That's our thing that says we're finished. 0 times 2 is 0. 1 minus 0 is 1. Remainder of 1. All right. Now, here's the one little trick here. We read our answer from bottom up. So the answer here is 10110001. That is the binary version of the decimal number 89. Make sense? And I promise you, if you go through the same thing we did the previous before the last break, and you convert that guy back to decimal, you'll get an 89. This is the ones place, 2s, 4s, 8s, 16s, 32s, 64. So 64 plus 16 plus 8 plus 1 is 89. Make sense? All right, so that's how we can convert from decimal to binary. What if I want to convert from octal? From decimal to octal. So all these are going from decimal to another base. What we looked at before was going from another base to decimal. So if I want to go from decimal to octal, let's take a decimal level. We'll just do 89. Do that one again. Okay, so 89 from decimal to octal. Instead of dividing by 2, we divide by 8. Okay? So 89 divided by 8 is an 11. 11 times 8 is 88. 89 minus 88 is a remainder of 1. 11 divided by 8, 8 goes into 11 one time. 1 times 8 is 8. 11 minus 8 is 3. One divided by 8, 8 goes into 1 0 times, so that tells us we're done. 0 times 8 is 0, with a remainder of 1. And then we read it from bottom up, even though in this particular case it reads the same both ways. But you do read it from bottom up. So this is the first value, then this, then this. So this is 131 in octal. Make sense?
Yeah, it is too long there, but it's short. Binary.
All right, so now let's do 221 from decimal to octal. You guys go ahead and do it. So let's look at this. 221 divided by 8. 221 divided by 8 is 27. 27 times 8 is 216. That's remainder 5. So 221 minus 216 is remainder 5. 27 divided by 8 is 4. 4 times 8 is 24, remainder 3. 4 divided by 8, 8 goes into 4 0 times. 0 times 8 is 0 with remainder 4. Read the answer from bottom up. So this is 435. It's the octal version of 221. Right?
It's a 335.
That's 3.
Did I do the math wrong here?
Because
This is a 3. 8 times 3 is 24. Yeah, there we go. So I couldn't multiply 8 times 4 is 32, right? It's too big. So 335. All right, make sense?
I'm asking about 3 divided 8 equal 0.
3 divided by 8. 8 goes into the 3 0 times. 8 does not fit into 3, right?
Yeah.
So that's 0. 0 times 8 is 0. 3 minus 0 is 3. It's a remainder of 3. Make sense? All right. Convert decimal to hex. So we'll start off with my favorite decimal number, 2989. Divided by 16. 2989 divided by 16 is 186. All right. 186 times 16 is 2,976. So that's remainder 13. 186 divided by 16 is 11. 11 times 16 is 176. So that's a remainder of 10. 11 divided by 16 is 0. 0 times 16 is 0 with a remainder of 11. So what's the answer?
C, A,
Yeah. So since we're dealing with hexadecimal, we need to convert these guys. This is a B. This is a A. This is a D. B-A-D. Make sense? Remember that one from earlier? We know that BAD converts to 2989 in decimal. We've done that one already, right? So it goes back and forth. Yep. Now, could we convert from decimal to base 31? Same pattern, right? You just have to use more of the alphabet potentially. Okay, so
this way or this previous way conversion?
it's an identical pattern. When we go from some base to decimal, we do it the other way, right? Where we start with the ones place, the next power, the next power, the next power. When we convert from decimal to a base, we do it this way. Make sense? All right, so now let me show you why octal and hexadecimal. So do we all understand the we can go both directions, right? So I can throw a curveball at you. Everybody understands going from a base to decimal, and everybody knows how to go from decimal to another base. So I'm going to give you a problem. Let's go binary to octal. So there's your binary number. So based on what you know right now, to go from binary to octal, you have to do two steps, right? You go binary to decimal, and then you go decimal to octal. Right? All right, so go ahead, take a couple of minutes. Give you about 5 minutes to do that. So convert that binary number first to decimal, using the first way we learned tonight. Then convert that decimal number to octal using the way we just learned.
Okay.
Make sense? All right, so the first thing we're going to do is we're going to convert this guy from binary to decimal, right? So this is the ones place, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256, 512, 1024. Right? So this is 1 times the ones place plus 1 times the fours place plus 1 times the eights place plus 1 times the 16s place plus 1 times the 64s place plus 1 times the 256 place plus 1 times the 512s place plus 1 times 1024's place. Notice I only did the ones because 0 times anything will be 0. Whoop. So that's 1,885.
Yes.
All right, so that gives me 1,885 in decimal. Now I want to convert that guy to octal. So that means we're going to divide that by 8 over and over and over again. So 1885 divided by 8 is 235. 235 times 8 is 1880. So that is a remainder of 5. 235 divided by 8. 235 divided by 8 is 29. 29 times 8 is 232. So that's a remainder of 3. 29 divided by 8 is 3. 3 times 8 is 24, so that's a remainder of 5. 3 divided by 8 is 0. 0 times 8 is 0 with a remainder of 3. So final answer is 3535 in octal. Everybody get that? All right. So,
I have a question.
sure, go ahead.
Now conversion from binary to decimal. Now here 1 multiply 1.
Yeah,
Start from
start on this side.
okay.
1 times 1,
Okay.
0 times 2. Notice I skipped it here because 0 times 2 is 0. So I left all the zeros out. So this is 1 times 1 plus 1 times 4 plus 1 times 8 plus 1 times 16 plus, skip, 1 times 64 plus 1 times 256 plus 1 times 512 plus 1 times 1024. I skipped over the zeros. This would be 0 times 2. This would be 0 times, what is this? 1, 2, 4, 8, 16, 32. And this would be times 128, which would give you zeros. So if you want to see it in here, this is plus 1, or I'm sorry, plus 0 times 2. See how 0 times 2 is not going to have any impact on the sum?
Okay, why is it plus 1 multiply 3?
Multiply by 3. This is base 2. This is the 1's place, the 2's, the 4's, the 8's, the 16's. There's no 3.
This is decimal.
This is binary.
From binary to decimal.
Binary to decimal, yeah. All right, so that's 35, 35. Now, did that take quite a bit of work to do? That was kind of a lot of steps, right?
Yeah.
You want to see the shortcut? Yeah. So I grouped them into groups of 3. And I just threw an extra 0 here in the front that doesn't change the value of it. So 0, 1, 1. That is a 3. 1, 0, 1 is a 5. 0, 1, 1 is a 3. 1, 0, 1 is a 5. So I just took my binary number and I split it into groupings of 3. And then I just threw the extra 0 in front of the 1 for visual, but you can leave it out. The 0, 1, 1 is the same value as 1, 1. Now, why did I break it into groups of 3? That's just a weird magic trick, and what's the legal alphabet for an octal value? 0 to what? 0 to 7. How many bits does it take to represent a 7?
Oh, just 7?
111 is the number 7, is it not? 000 is the number 0. So with 3 bits, I can represent all of the octets, all of the values that are, all the alphabet values for octal. Make sense? So octal, you do groupings of 3, and then you just convert those 3 binary bits into their decimal equivalent. Well, in this case, it is their decimal equivalent, but this will come out to the octal value for it. So this 3-bit number, 101, this is a 1 in the ones place, a 0 in the twos place, a 1 in the fours place. 4 plus 1 is 5. That's where this 5 comes from. 0, 1, 1, that's a 1 in the ones place, a 1 in the twos place, and a 0 in the fours place. So that's a 3. 101, this is a 1 in the ones place, a 0 in the twos place, a 1 in the fours place. That's a 5. 011, this is a 1 in the ones place, a 1 in the twos place, and a 0 in the fours place. That's a 3. See how that works? Okay. Let's convert binary to hexadecimal. Let me think about this one for a second. All right, so convert this binary number to hexadecimal. Do it the long way. If you know the trick, don't use the trick. Okay, do this the long way. So you're gonna well, you can use the trick if you want, but I want you to practice this time. Bet you're gonna have a quiz next class. This number conversion stuff. So first convert this guy from binary to decimal, then convert your decimal to hexadecimal. Okay? Take a couple minutes, do that. All right, so for starters, we need to convert this guy to decimal. So that's a 1 in the ones place, plus a 0 in the twos place, plus a 1 in the fours place, plus a 1 in the eights place, plus a 0 in the 16s place, plus a 1 in the 32s place, plus a 0 in the 64s place, plus a 1 in the 128s place. 2s, 4s, 8s, 16s, 32s, 64, 128. Plus a 0 in 256, plus a 0 in 512, plus a 1 in 1024, plus a 1 in the 2048. And this should give us 2989. Nope, I did this wrong then. One in the ones place, twos, fours, eights, 32s, 128, 256, 512, 1024, 2048. So you have 3,245?
Yeah.
Oh, then I gave you the wrong number to begin with. I messed up there. All right, whatever. All right, so then we're going to convert 3,245 to base 16. So we're going to divide that by 16. 3,245 divided by 16 is 202. 202 times 16 is equal to 3,232. So that's 13, remainder 13. 202 divided by 16 is 12. 12 times 16 is 192. It's remainder 10. 12 by 16, or 12 divided by 16 is 0. 0 times 16 is that. Remainder 12. Oh yeah, I was off by 1 on that one. So then you convert these. This is C. This is A. This is D. I meant for it to be bad, but I wrote the wrong binary number. So this is CAD is the final answer. All right, and then the shortcut for this guy is you break this guy into groupings of 4, because the legal hexadecimal values are 0 to 15. 1111 is a 15. 0000 is a 0. So 4 bits gives you hexadecimal. So there's 1, there's 2, the other one. So I wanted this first guy to be a B. So this is a 0 in the ones place, 2s. This is a 4 plus a 8. So this is a 12. So that's a 12. Ay, ay, ay. This is the 10. This is a 13. Or C, A, D. So this guy needed to be, if I wanted him to be an 11, that's an 8, 9, 10, 11. That's what I should have written the binary number as to get you the B as the first value. This would be an 11 then. All right, questions about any of that? All right, your homework for next class, and for those of you who didn't get the Mendix thing done, go ahead and finish that. Homework for next class is in the book, CSC535. Now, as you go through this, there are interactive exercises that you get graded on, and you can keep redoing them until you get full credit. So I would presume you would do them until you get full credit. So go through chapters 1 through 5 for next week, doing all the interactive activities in those. Sound good? So this is introducing you to Python. So last week you were using Mendix, which was a kind of a tool that took you through doing stuff with a drag and drop interface. Now you're going to be going through and learning Python, which is going to introduce the syntax side of things. But you're going to go through something very similar to what you did with Mendix, except you will come up short of microflows, because functions are kind of where microflows are. So in terms of the amount of work you should do for the week, chapter 1 through 5 is what you'll work through. Sound good? So chapter 1 through 5 for the book, what I'll go ahead and have you do is submit screenshots at the end of each chapter, just so you have something to submit, because I'll be able to go in and look at what you've done in the book. I just need something to be able to grade. All right, so I'll put a Dropbox up. I'll say, work through chapters 1 through 5 in the book, submit screenshots at the end of each chapter, and then that'll give me something I can then go and grade. But all your stuff will actually be stored up on the Zybook. When you complete those activities, I'll be able to log into Zybooks and see your completed activities. Make sense? Questions? Comments? Who? No, it's called Zybooks. It was on the syllabus, and you were supposed to have already bought it. You'll be able to get it in real time. You don't have to wait for anything to ship. But this is an online website. So if you aren't familiar with what I'm talking about, We did talk about it last class when we went over the syllabus, and it is on the syllabus. So go and look it up. Sound good?
$60.
Well, whatever it is.
Is it?
I don't know what it is. It's whatever it is on there.
I'm asking.
I don't sell the books. iBooks does. I don't know what the price is. Go and look it on there.
It's like, yeah, you say that last.
Yeah, so that's probably correct. That sounds about right.
I think